All right, we'll take a little refresher back to strength of materials, and we'll talk about beam mechanics, since this is going to be our first topic of, first type of member that we look at in reinforced concrete will be a beam. Let's go back and review general beam mechanics. This is a topic back in strength of materials. Basically, we said something like this. We have, a beam, and it has loads on it, and that beam's going to bend. All right? When we look, back at statics, we could calculate the reactions. Once we had that in strength of materials, we could develop a shear diagram and a bending moment diagram. When you have a beam that has a bending moment applied to it, and again, that moment that's applied to it is really the moment off the moment diagram at some location. The beam on the inside has to resist this outside applied bending moment. The way it resists that is it develops bending stress. There's a place in the beam, on the beam's cross section, that doesn't have any stress at all. Doesn't have any strain. That point is called the neutral axis. On one side of the neutral axis, the beam's going to be in tension. The fibers of the beam are stretching. On the other side of the neutral axis, the beam's going to be in compression. The fibers are being compressed or shortening. Okay? Those are strains. When you look at the length of an element, or whether it's and then what distance it's stretching or compressing, change of length over original length, that's strain. Well, strain also is accompanied by stress. So on one side of the beam, you're going to have a bending stress. That's actually, a tensile type stress. And on the other side of the beam, you're going to have a compression stress. Now, in a homogeneous beam, isotropic cross-section, homogeneous, everything's perfect. We talked about these stresses being sort of triangular in nature. If this was a 3D drawing, you'd see sort of a wedge of tensile stress on one side of the beam and a wedge of compressive stress. If I just took all those stresses and lumped them into a single force, I could call that force like a T force, tension force. If I took all my compressive stresses and lumped them into a single resultant force, I could call that a C force. So these bending stresses that are developed by a beam on the inside really develop a tensile resultant on one side and a compression resultant on the other. What can you tell me about the tensile resultant versus the compression resultant? They're equal to each other, right? One's going one way, but it's equal to the other going the other way. They're separated by distance, right? We'll just call that distance the arm, the moment arm. Okay? Two forces that are equal, separated by a distance. People in statics call that a couple. All right? But what does that couple do? It creates a moment the other way. That's how a beam works. You got this external moment coming from the loads on the beam. The beam on the inside of it has a resistance that we call bending stress. But that bending stress is developing a moment that's going to exactly be equal to that externally applied moment, the moment that comes from the loads. So if think about this, the loads on the beam produce a moment that's 100 foot kips. The beam itself on the inside has to produce a bending stress. The bending stress, the net result of it, has to be such that it produces a moment of 100 foot kips too, or if it doesn't, what happens? It fails. You know, you don't have equilibrium. It falls down. That's it. That's the way, you know, generally speaking, back at strength of materials, we talked about beam behavior. It's all about equilibrium. You know, forces produce moments. Moments are at this location on a beam. That beam has to generate a bending stress at this location in the beam that has to be exactly equal to it, and opposite, equal and opposite. All right? Okay. Questions?